Hello everyone, welcome back to 25th video of our Biopharmaceutics challenge. So today we are going to discuss one compartment modeling in which we are specially going to focus on the IV bolus administration. Now in the previous video you must have seen the compartment modeling basics, right? What parameters we need to do. So today we have the one compartment IV bolus, right? So what does this IV bolus means and what does this IV infusion means? What does this extravascular administration mean? So we have IV bolus, that means all the dose will be administered all at once, right? IV infusion means we have to infuse it at a controlled rate in your body. So the infusion rate must be considered. So in the case of IV bolus, as all the dose is administered all at once, so that is why there is no rate of input that is mentioned here. Otherwise, if it was rate of infusion, so we must have to add the rate of infusion in the rate of input, right? So in the one compartment open model, which is also known as a single compartment model, in this the drug is administered by IV bolus route. So it takes about 1-3 minutes to complete the circulation, and hence the absorption rate is neglected. For a general compartment modeling, you must have seen that we add a rate of input and the absorption rate Ka, and the elimination is generally Ke, because the dose here generally we assume that the rate of absorption is generally neglected. So if you must have to enter the rate, that must rate in minus rate out. So here, as it must be Ka into X, but now the rate of input is 0. So only the rate of elimination is considered. So we have dx by dt is equals to minus Kex. Only important thing here is going to be your basic, that is the equations that are confusing to some students. So please note them down one by one. This is the first equation that we got, right? This is our first equation. In the upcoming videos, I'll be putting the MCQs of each topic which we have discussed till now with its explanation, so that you can have a better idea of 5 to 10 MCQs from each topic that will mark as important. Okay, so we have a simplest representation of the one compartment where the drug is being administered. We have the compartment considered as blood and other body tissues, and Ka be the rate of elimination. X here is the amount of drug that has been administered, right? So using these general expressions, we can calculate the other pharmacokinetic parameters. Here you can already see, I'll write it here if it is not clear to you all. So we have to put the rate equation as rate in minus rate out. This is what is mentioned here. So finally we will be left with the rate out, that is referred to as here minus Kex, right? So this Ke is going to be the first order elimination rate constant. This X is going to be the amount of drug in the body at a time t. So the negative sign here indicates drug is being lost from the body. Okay, now we can estimate our pharmacokinetic parameters using these equations as follows. Okay, let's see what pharmacokinetic parameters can we follow. We can calculate the elimination rate constant, we can calculate elimination half-life, we can calculate clearance as well. So number one thing, you have already seen the equation. Now that equation can be put up into a simpler exponential form, that is x is equals to x naught e raised to the power minus ket, where x be the amount of drug at time t and x naught be the initial amount at time 0, right? We have elimination constant and t raised to time, right? Then we can do the logarithmic version of that, right? Similar equation is converted into just its logarithmic form. Using these equations, we can really put them into the values of the simplest forms. Here you have just converted the into the logarithmic scale. So we have put it as log C is equals to log C naught minus KET 2.303. You can just write it as log X is equals to log X naught in order to maintain even more efficiency, right? So other than that, what can we follow here? What can be written here? You can see we have elimination half-life as well. You have seen prior to that it follows first order. It follows first order. So definitely the elimination half-life is going to be T half is equals to 0.693 upon your Ke, right? So all those who know about the formula, very simple formula of clearance, that is what? That is clearance is equals to KE into VD. KE elimination constant, VD will be volume of distribution, and clearance is CI, right? We can substitute this into this formula as well, whereby you can put the value of KE as clearance upon VD, right? So put this value here, we get T half is equals to 0.693 upon clearance into VD. So you can get the values of multiple pharmacokinetic parameters using the same equations again and again. See, using these three equations, we have already added these values. So you got T half, you got KE values, and you got the clearance value by this one compartment IV bolus. Thank you so much. We will meet in the next video for one compartment IV infusion. Okay.